Hello everyone, today we are interested in understanding transfer learning with MATLAB. Let's just go ahead and dive right into it. MATLAB has made this simple with the use of Deep Network Designer app, which is part of the deep learning toolbox. We're just going to go ahead and try an example real quick and see how this works out. Let me just resize the window. It takes a minute or so. Remember, transfer learning is about using a pre-trained network that's already been trained over thousands and millions of images for hundreds of objects for you. And the idea is to simply make some changes, small changes in the already pre-trained networks to suit to your requirements, to your data sets, so that you could deploy your network very quickly, making use or leveraging the already pre-trained weights on the network. Okay, so we're going to go ahead and look into SqueezeNet and modify this according to our data set and try to see the kind of results we can get to it. Remember, if we begin from scratch, we might need millions of images and hours of training this network, but once it's already been done, it's already been trained, the network is familiar with seeing certain objects, 1,000 in case of SqueezeNet. So what we could do is simply modify it slightly, feed in our dataset with only a few images, maybe hundreds or 50 or so, instead of millions that would have otherwise been used for initial training. So we could use a small data set to train it, further optimize it a little bit, and get good results from this. Okay, so that's the data set. You could always that's the network, and you could always zoom in to understand its structure better, what kind of layers are present over there. But our concern with this mostly is to just modify two layers towards the end. One of them is the convolutional layer and the other is the classification layer. Remember what the convolutional layer essentially does. It simply if I could move to this window, it simply goes and performs convolution. But the idea in convolution, remember, is that you have an image and you're applying a filter to it. Okay, and then that filter is simply going to spatially convolve with this image, resulting in scalar outputs. So you get, so this filter, when spatially convolved with this image, which is a three-dimensional image and a three-dimensional filter, at this point in time is going to yield into one scalar output. Then the filter is going to move a pixel here, the center of the filter is going to move a pixel to the right, and then there's going to be another scalar output, and then towards the right, and then another scalar output, and eventually the filter is going to slide around all the image, resulting in a scalar output image that is going to be of one dimension. It's going to have a single channel because it's a scalar product. It's going to it's a dot product, it's a scalar output, so it's going to give you one frame or one dimensional output. Okay, which is going to be something like this. Okay, 28 by 28 results from a 32 by 32 image. Is largely because we assume that the filter is not moving out of the frame, it's just the corners are touching with the corners of the frame. The center of the filter does not move out or towards the corners. With that being the reason, we disregard the 2 pixels on the periphery on either side, so the 4 pixels get basically ignored, resulting in a 28 by 28. But in convolutional layers such as the one that we have in this network, it tells you there's a number of filters of 1,000. Okay, and the filter size is 1 by 1. Yes, that's okay to have 1 by 1 filter size. Essentially it's just going pixel by pixel instead of 5 by 5 filter size. But when you look at the number of filters, that's 1,000. And if you look at the classification classes, those are also, the output size is also 1,000. Basically the idea is that you have the number of filters equal to the number of classes that you have in your data, or the number of classes that you want your network to classify, basically. That follows because each filter is resulting in a feature map per se, corresponding to each class. So if you have, for example, 6 classes, you would independently convolve the image with each of the filter, resulting in a scalar frame from each of these convolutions with these filters. Okay, so the resultantly you would have 6 images. Obviously they're stacked, each one is coming from the convolution result of each filter, and these are done independently. Okay, so that's the idea right in. So when we want to modify this layer, we're essentially wanting to modify the number of filters, basically. Okay, so if and I know the my dataset has 5 classes, so I would want the number of filters to be 5 right here. If I cannot make changes here, I would just go ahead and remove this, set up a convolutional 2D layer right here, make sure I have these connections in place, align it, and have the number of filters as 5. Because I have 5 classes, filter size I would keep it as 1 by 1. Then other thing is then the classification layer that I want to change, because I know I have 5 classes in my data set. I don't want 1000 classes. If you want to find anything, you could simply type in, drag and drop, make sure you connect them, and there you are with your classes. So I didn't have to type in 5, it's going to take the number of classes and their names automatically from the dataset that I'm going to provide. So let's just go into the dataset and import our data. So you need to provide paths to the folder where your data is, and if I can just simply, yeah, there it is. So if I go ahead and see, I'm going to provide this folder name, and it's going to take the label from the folder names that are present within it. So I have to provide paths to this basically, and here are my 5 classes: apple, candle, oranges, pens, and plants. So and I have images in for each of them. Okay, but I'm going to provide the path for precisely this folder, and it's going to get these. Alright, so let's just provide that. Some of the augmentations that you could do, perhaps move or tweak and twist your images to allow your network to be better prepared to see images or classify them in case they are rotated by some angle. So it's always okay to introduce some sort of augmentation in your data sets. Other than that, you have your percentage that you could specify that you want to divide your data into training and testing sets. So we have images that we use for training the network, and then we could leave out some of the images to test it later on as a validation data set. Okay, so we don't let the network see these validation or testing images. We only familiarize the network with the training images. Okay, so that's the percentage that you want to split your data into. So 30% of the images from the entire data set we would want to keep for validation. So once you've done this, just click on import, and then you should get a distribution of your data. So you have the number of images here, and then the labels of those images, which are taken from the folder names that have been set up. Okay, and these could be unevenly distributed, and that's okay. But once you're done, you move into training, some training options that you need to set up. Of course, we do not have many images. We had about 15 or 20 or so for each object, but the more the merrier. Obviously, if you have more images, you would have a better training process set up. Some of the things you could change here, but I would consider leaving them as they are. I would maximum networks, maybe I would set this to It's okay to have it, but it might take time. Either way, if it takes way long, I'm going to go ahead and edit the video anyways. So let me just set this up to something smaller regardless, and we can go with a smaller learning rate maybe. Okay, so once those have been set up, you're just going to go ahead and train the network. In case this takes long in my machine, because I have a screen recording going on as well, I will edit the video and report how long it took. Alright, so we are done here, but there's something graphically not quite okay as far as the loss is concerned. Let me just resize the window, maybe yeah, okay, so I just resized the window and it got better. If I could perhaps resize it a bit more to make it look even better. Okay, but regardless, we have a bit of information right here. You have elapsed time information as well, but it took me about 5 minutes or so to get the entire process done. The other thing is that look at the validation accuracy that we have received for our entire setup. So we managed 100% validation accuracy. Remember the test and the training data split that we made? We made a 30% split. So the 30% of the testing images have in fact all being correctly classified, okay, by the time our iterations reach to the 10th epoch. So that is good news, and therefore the loss approached zero. So that is in fact perfect results. But if you choose different learning rates, and obviously with different or complex and depending on your data set as well, the kind of images that you take, you could have different accuracies as well. So that being said, the other thing that we would want to do from this point in time, so of course we have these results here, but these are kind of locked in. So what you would want to do is mess around with the code a little bit, just to see that if you have an image now and you want to see if it classifies it correctly, or what does it classify to actually, you might be interested in that. So let's mess around with the code a little bit, see how to classify an image based on this new learned network. So we could export our results and export the trained network essentially, and we could also generate the MATLAB code for the entire process of importing and training that we did from the UI. Okay, so this has been exported to the workspace. So let's just head to the workspace, and we have our network exported here. Remember, in the test cases, what we have is just a set of a few images that the network has not seen before. So we're just going to see whether or not this is actually an apple classified by the network, exactly an orange classified by the network, etc. Okay, so let's just see if that is really the case. What we would want to do is go into this. We are in the right directory. We want to read in all these images and then one by one feed it to the network and then classify them and see what kind of classification results the network gives us. So ideally what you would want to do is use an imread command and store this into an image, but you want to read them one by one. The way to perhaps load them all together would be to use, because they are all JPG images, so you could maybe store them as images in a directory. Let me just do this in the command window and then lock them in the editor as I go by. Okay, so we get a structure of images. What it has a lot of information, but we're interested in the name, and there are 10 images. So okay, it's 10 by 1, 10 rows. So if you want to read in, so each row has the name. Under the name banner, each row has the name of the image basically. So I am in fact going to do dot name. Okay, if I want to read in the first image, I am just going to go ahead and choose the first row and its name property, feed into imread, and it should give me the image that I am interested in. yes, in fact it does. But the problem with this is a 3024 by 403 2 by 3 image, and if we look at SqueezeNet, in fact has is an image input size that I'm interested in actually. Okay, it doesn't list it here, but the image input size for the pre-train, in fact we do have it somewhere around. Let me open up the editor again, the network app again, no, the designer app. So if you go back to the designer and look at the image input size that this network is trained for in the input layer, you should see it 227 by 227. Yes, that's what I'm looking for. This network is basically trained to receive image inputs of 227 by 227. So when you feed in this input size image, it's not going to accept it. Okay, so we need to do a resizing of the image. Okay, so we could just go ahead and resize the image as this. Okay, so we're going to feed in IMG, resize it to 227 by 227 and store it as I maybe. Okay, let's just maintain, yeah, it maintains the third dimension, and that's what we need, 227 by 227 by 3. What we need to do next is then basically use a simple classify function. But the classify function is going to need to know what to classify and through what network. So we are going to use the trained network, which is our network, and we're going to classify image I. Okay, the result of this has to get into two important variables that we are keen on, one of which is simply the prediction, the other is the probability, okay, of those predictions. So let's just go, but before we go, let's just see what is in there. So you have a set of layers, you have connections, input names, that's just data, output names, this classify out takes automatically. You have list of connections that are there between the layers. So this is basically just a structure of what we graphically saw, and then a list of the layers that are there. Okay, so anyways, classify is the function that we are using. Trained under network underscore one is basically the name that we got from the GUI. We exported it into workspace. I is the image that we want to classify. Let's just run it and see what do we actually get. So we do get a probability and we do get prediction. So this is categorical, it predicts it correctly, and it how do you know the prediction of the apple? So there it is. Okay, but how the apple prediction is 0.9, so that's a very strong probability, and that's and the other four classes are very low. So what you basically do is if you wanted to extract the probability with which it was predicted, it's probably take the maximum one. Okay, so if I could just in fact just do a that is in fact an apple, but what I want to maybe do is store its let's give the title to our image. What should, let's just give it, we already know what the prediction is, so let's just give it this as a title, and then maybe we would want the probability, those are as numbers, so we could this is going to in fact give all 5 of them. What we are interested in, probably the first one, or the maximum one, because the most probability of the higher the probability, that's the prediction. Okay, so that's what we would be interested in. What else? Maybe the num to string needs degree of accuracy. Maybe we could keep it to 2, and then it should be okay. It's not superver types of category. Interesting. Alright, now we are good to go. Okay, Apple 0.93. In fact, let's just space, multiply this with 100. Assign some percentage, assign to it. And use that for a better representation. So Apple 93%, that makes sense. But let's just do this in an iterative loop. We already have everything in IMGS. What we need to do is perhaps set up for whatever the length of IMGS is. I only have 10 of them. Let's just hard code it for now. So we have Apple, and then the second one is detected as another Apple, but with lesser probability, 76%. Third is Orange, 99%, fairly nice. Orange 87, Candle 93, Candle 92, Pen 94%, Pen 82%. Remember how these are rotated as well, and still they are recognized very nicely by the network. So that being done, I hope this was useful. For any queries or suggestions, happy to answer in the comment section. Thank you.